Welcome to the next lecture in our System and Devices 2 networking module. In this lecture we will be going down that protocol stack down to the transport layer, layer 4. Okay, but before we do that, let's have a quick reflect on what we did in the previous lecture. So at the end of the last lecture, I asked you to go away and have a look at NTP, our Network Time Protocol. Read the RFC 958. So fingers crossed, touch wood, you identified that the actual time is represented as a fixed point value. So as always, if you want to know more about protocol, you go to the RFC. So if we look at the RFC for one moment, we can see that time is represented as two 32-bit values as a fixed point representation. So you have 32 bits representing the integer part and 32 bits representing the fractional part. So depending on the version of NTP, the one in the lab will be using 32-bit values. So you have 2 to the 32 seconds and 2 to the minus 32 fractions of seconds. So you can represent values down to a couple of hundred picoseconds worth of resolution. So time within an NTP packet is just a number. Therefore, to relate that number to a time, it's an offset from a base date measured in seconds. So time started for NTP on the 1st of January 1900. And it uses the UTC time standard, so Coordinate Universal Time. So you might go, well, okay, hang on a minute. So why is it UTC and it's Coordinated Universal Time? So why isn't it CUT, the French? So we had to agree an acronym that would be consistent across all languages and the French one. So their pronunciation of it is Universal Time Coordinate. Yep. Okay, so as you probably can spot, if we've got a fixed point representation, an offset from a starting date, then problems will going to occur when we max out our fixed point value and we overflow back to 0. So we've got something similar to a Y2K bug. So for those who haven't come across that one, 25 years ago now, back in the early days of computers, to save a little bit of memory, we only represented the year as 2 characters, so the last 2 digits. We didn't bother representing the 19 or the 20 because that'll never happen. The software will never be running for that long, surely. So when we got to 99 and we rolled over to 2000, the system went back in time, so all the dates would be wrong. And it was prophesied that planes would fall from the sky and nuclear reactors would explode. But we survived, so it wasn't as bad as everyone thought it may be. But obviously a lot of money and work went into checking these systems to ensure that they would update correctly. And a similar thing is going to happen with NTP. Obviously at some point we'll max out our count for the number of seconds and it will overflow back to 0. So the time on all our computers will go back to 1900 again. So depending on your version of NTP, the doomsday date is the 8th of Feb 2036. So add that one to your calendar. As I said in the last lecture, we'll be looking at NTP in a lot more detail in the lab. So do go and have a look through this one. There's a couple of assess questions there to test your understanding of NTP. So you'll be using the NTP server that is running on Pi 1, and that's synchronized to a real-time clock module on that Raspberry Pi. But to allow your NTP server to synchronize to a more accurate clock, you can connect to the lab's network and connect to the GPS NTP server as we looked at the end of the last lecture. Okay, so that's where we were. So in this lecture, we're going to look a little bit deeper down our protocol stack. So we're going to go down to the transport layer and start to consider why we need 2 transport protocols. Why do we need UDP and TCP? What capabilities do they give us and why is that significant? However, before we start on that journey, just to reassure those nervous people that you don't have to worry about the upcoming apocalypse. As if you believe in time travel, this has already been sorted out. So John Tada has already come back in time and using an IBM 5100, he saved the day. There were posts on discussion boards in 2000 about a person who claimed to be from the American Military Time Travel Division, and his logo is shown here, and he was requesting an IBM 5100 so that he could take this computer back in time and fix some legacy systems to stop the world disintegrating down into chaos. So all our problems have been solved if you believe this. Some people say the logo looks very like the Star Trek one, but I'm not so convinced. Maybe there's some hints there. So maybe there's some inspiration in later Star Trek episodes. I confess, I find this an amusing story and I do like that computer. An example of an early portable computer with a built-in keyboard and monitor and a tape drive. I remember when I was doing my work in electronics department, we always backed up onto the tapes like this. 500 megabyte tapes back then, and that was enough to store multiple copies of all the work we were doing, because the hard disk for the computer back then was less than 100 megabytes. Those were the days. Okay, so as I said, we're going down our protocol stack. We're going down to layer 4, going down to that transport layer. So applications deal with messages, and those messages will now be broken down into segments, and those segments will be transferred across your network, so passed to another machine. So at this layer, we're dealing with how we move these segments from one host to another across our network. So think about error detection, retransmission, corrupted packets or lost packets, equally congestion control. So how do we regulate the usage of the network? So how do we stop one person hogging all the network? So at this layer, there's a number of different issues that we need to consider that we just ignored at the application layer. But you've got two choices. You've got the Transmission Control Protocol, TCP, which is connection-based protocol, a reliable protocol, which handles all that retransmission of lost or corrupted packets and has systems in place to minimize congestion control. So quite a complex protocol. And obviously that comes with associated processing costs. But if you want to take the other extreme where you ignore all these issues, we can use User Datagram Protocol or UDP. It still does error detection, but if it detects a packet is corrupt, it'll just drop it. It won't ask for retransmission. And it won't stop you flooding the network with lots of packets if you so desire. So a very simple protocol, a very minimal protocol, a connectionless protocol, a unreliable protocol. And each has their place, depending on what you're trying to do. Okay, to start us off, to help explain these concepts and identify the things that we should be considering, we'll be looking at IP over AC. So this was developed in the early 90s, and you typically see RFCs coming out around April time, especially April the 1st. And if you look at some of these RFCs, you'll see the joke. So this is IP over avian carrier, or using carrier pigeons to carry our packets. But it does start to introduce some of the concepts that we will be looking at in more detail with TCP and UDP. And it's a good place to start. So we have our IP protocol, but rather than being transmitted across copper cable or as light pulses down fiber optic cable, our packets will be put into a little container on our pigeon's leg, and obviously they'll then fly to their intended destination. As you can imagine, if you're sending your message using pigeon carriers, you'll be sending multiple packets at the same time. So you'll have multiple packets in flight at the same time. And obviously these pigeons will arrive at their destination, maybe out of order. Obviously during their flight, you may suffer packet losses, unfortunately. So there may be human intervention that loses packets, or natural noise in the environment that results in lost packets, unfortunately. So these are the things we need to consider when we're designing our protocol. Equally, there'll be intrinsic delays that we need to consider during this transmission process. So if it took, for example, if we were transmitting a message from London to Edinburgh, it'd be unreasonable to make the pigeon fly that in one go. So maybe that packet will be routed via Manchester, somewhere in the middle. So you have to consider the process of delivering that segment, to delivering that message carried by the pigeon. So there'll be a number of delays associated with the transmission of that packet. So our processing delays, one way to consider that, delay incurred by putting the message into the container. That is your processing delay. Equally, there may be some delay in encrypting that message. So you might have that manual step where you need to convert the raw text into an encrypted form before you load that little canister with the message, the packet you want to transmit. Equally, there'll be queuing delays. So you load up those messages onto your pigeons, and then you want to release those pigeons, and obviously they'll be going through the hutch in their coop, so they can't all exit at the same time. They'll have to go out in a particular order, so there'll be delays associated with the queue before they're released until they can take flight. Equally, you'll have queuing delays associated with pigeons arriving, so the pigeons arriving at their destination. Obviously, you could have multiple messages being transferred, so the pigeons arriving could be carrying segments from other messages, from different messages. So these pigeons would also need to be added to the queues to be processed. Then finally you have your transmission delay and propagation delay, and sometimes a little bit confusion what those two terms mean. So for me, transmission delay is how long it takes to transmit the message. So you've got your packet, you've got your pigeon, how quickly can you pick a pigeon from the coop and throw it out into the air? That's your transmission delay. So how quickly you can throw pigeons into the air and you don't get, obviously, too fast that you start to shoot down your pigeons with other pigeons, so you don't get any mid-air collisions. And that differs from the propagation delay, and the propagation delay is the time it takes the pigeon to fly the distance. So how quick is your pigeon? And obviously some pigeons will be quicker than others, depending on the path they take. The time it takes to go from London to Manchester, for example. And obviously that's different to the transmission delay. So propagation delay is how fast the pigeons can fly. Transmission delay is how quickly you can move the pigeons, if that's not too many pigeons. So basically you end up with this equation down the bottom here. The time it takes to transfer your message is dependent on the number of stages, the number of hops. So in this case here, we've got 2 hops. We're going from London to Manchester, and then from Manchester to Edinburgh. And then at each stage, you'll have a processing delay, queuing delay, transmission delay, and a propagation delay. So the time, the end-to-end time is determined by the number of stages. And at each stage, you'll have a processing delay, a queuing delay, transmission delay, and a propagation delay. So your processing delay is dependent on your software and hardware running on your system. Your queuing delay is a little bit of an unknown. Obviously, that's dependent on traffic in the system. So how many other applications, processes are trying to use the network at the same time? So how much is being received and transmitted by other programs? Because obviously the network is a shared resource. Transmission delay, as we see here in this equation, depends on the number of bits you're sending, how quickly you can send those bits. So your length of your data packet in bits, and your data rate, how many bits per second can you send? And your propagation delay, and in networking we call that time of flight, which is particularly appropriate for our pigeon analogy. So the propagation delay is dependent upon the distance and speed. So if we have our pigeon flying from London to Manchester, what is that distance? What is that straight line distance? And how fast can our pigeon fly? So distance divided by speed. So hopefully that made sense. To see if it did, we have a quick quiz. So we'll move away from pigeons back to normal technologies. So we have a communication link between 2 machines, our client and our server, and that will be going through a number of communication channels and through a number of networking devices, so switches here. So devices that will be implementing our packet switch network. So remember, these are store and forward devices. So the whole packet has to be stored in the switch before it can then be transmitted to the next hop in its journey. So again, if we go back to our pigeon analogy, you don't receive half a pigeon. That would be a bit messy. So the whole pigeon has to be received in the switch. The whole packet has to be received in the switch before it can be processed and then forwarded on to the next hop. So each of these communication channels will be of a certain length, some short, some long. You can assume that the speed, the propagation delay through that communication channel is consistent, 2 times 10 to the 8 meters per second. Obviously, you can approximate the propagation speed to the speed of light, but obviously that's only true in a vacuum. So when you're transmitting signals down cables, it's limited by its electrical characteristics, so its resistance, inductance and capacitance, for example, if it's copper, or its refractive index if it's a fibre cable, and the type of fibre cable. So there's always a few subtleties there. So the packets we'll be sending are 1,500 bits long. Using this and making some assumptions, what is the transmission and propagation delays of each stage, and what will be the end-to-end delay for transferring this packet? And as always, we will be going through the answer in the lecture review sessions. Okay, just to take a moment to pause and consider what we're actually talking about when we refer to the transport layer. The transport layer exists between the client and the server, so from the client to the server in this diagram, forming a logical connection between these 2 hosts that the application layer can use to communicate data, to pass segments between these 2 machines. So when we look at the transport layer, we're not concerned about how the packets get from point A to point B. So using the pigeon analogy, what path the pigeon takes, does it fly, does it take a car? Those are decisions made by the lower levels in our protocol stack, by the network layer. Does the packet go across a copper connection or Wi-Fi? We don't care at the transport layer. We're just conceptually forming a link between 2 machines, a transport layer on one machine to a transport layer on a different machine. We're creating that end-to-end communication link. Again, shown in this diagram, we'll have some devices that implement our packet switch network, so some routers, some switches, and obviously we don't have to necessarily go up to the transport layer in those devices. For a router to route packets, it doesn't need to know anything about the transport layer. It just needs to know about the network layer, about IP packets. A switch, it doesn't need to know that. A switch will work at the link layer. All it knows about is MAC addresses. We'll look at those later. There's not necessarily a transport layer in one of these devices. You can see I'm hedging the bets here. Nowadays, routers are managed devices, so they'll have a web server running on them. They'll have a web interface to allow you to manage that device. So that's a different question. But to implement the desired functionality, that is to route packets across a network or in between networks, we will not be going up to a transport layer in these devices. It'll be going up to the network layer for a router or the link layer for a switch. Okay, so the first protocol we'll be looking at that exists in our transport layer is UDP, so User Datagram Protocol. So as always, if you want some more information, RFC 768. Within this documentation, packets are referred to as datagrams, but that terminology is also used in the network layer, so I'm going to avoid that. All our messages will be broken down into segments, so that's the units of data within the transport layer. Is a segment, and you'll see that in many a textbook. It's a common way of describing our data at this level. So say an old protocol created in the 80s, 83, and it's a minimal program. It's a connectionless protocol. It's an unreliable protocol because it's very simple. So if you use this protocol, there's no error handling in the sense of retransmissions. It can detect if there's an error because it has a checksum here. It has something you can test to see if your packet has been corrupted, but if it has been corrupted, the receiving machine will just drop that packet. It won't ask for a retransmission, as that will require extra data fields. We'll see that later when we look at TCP and additional processing. As I say, it's a connectionless protocol, which means that you don't have to test to see if the receiving host is ready to receive the data. It's, as it says there, a fire and forget protocol. So you can create a UDP packet and send it onto the network even if the receiving host has been turned off. You don't have to create that communication channel, that connection, before sending the data. So a UDP packet, a UDP segment is constructed as you see here. So we have 8 bytes of header, and then you have your data that you want to transfer. So the key thing that identifies at the transport layer who's talking to whom is your source and destination ports. So again, if you consider our NTP protocol, if you're connecting to our NTP time server, you'd be connecting to destination port 123 because NTP uses UDP packets. So these two ports identify who is communicating to whom. In addition to that, you have a length field and a checksum. So the length field is the number of bytes, including the header, so your header length plus your data length. And the checksum, we'll see that later, is a way of generating a number that allows you to check if there has been any bit flips, any corruption due to noise, etc. during the transmission of this packet. But the key thing, as I say, at the transport layer, you're communicating between 2 ports. So on your 2 machines that are communicating across this logical link, you'll have your client and your server, for example. So you'll perhaps have some processes that want to transmit data, transmit segments onto the network that will be received by processors, servers running on the server, a different machine. So it's these port numbers that identify who's connecting to whom. So as we saw at the end of a previous lecture, these port numbers define particular ranges. Obviously they can be, if you go back and look at the header value here, these are just 16-bit values. So in theory there can be any value from 0 up to 64K, but obviously some have been reserved for specific applications. So port numbers 0 to 1023 are standard ports, or your system ports. So port 123, for example, fits within that range, which is your NTP server. And then above that, the range does vary a little bit as your register ports. So later applications have been assigned port values within this range, and your higher values are ethereal ports that will come and go but are used during the communication process. So to kind of show that one, we'll come back to this diagram here. So I say at the moment we're not worried about how it knows how to connect these 2 machines together. We're just looking at devices in this transport layer. So the thing that defines this connection are your port numbers. So your source port and your destination port. So let's, for example, let's say we've got some telnet server. So over here on the receiving machine, we've got a process, we've got a program running, so you can connect to that. And you'll connect to that through your socket, through your port, and assign the system port number 23. And it's always 23. So that's how you know you're connecting to the telnet server, because it will be port 23. On the transmitting machines, you might have multiple telnet sessions. And obviously they'll all connect to port 23, but to uniquely identify which of these telnet processes is communicating, obviously each one of these will be assigned a material port number, a different port number. So let's say 8000, 8001, 8002. So they all have the same destination port number, but they'll have different source port numbers, and the combination of the two identifies who is communicating to whom. So each of these processes want to communicate across the network. So you'll pass the data you want to communicate through your socket, and obviously that will then be managed by the transport layer, because you've only got one network connection, passed down the network stack. So all these segments will be transmitted across the network, received up the other end. It'll identify where they're going to based on the port numbers, and identify who is talking to that particular instance of the telnet server via that source port that is within the UDP header. And for the moment, we'll ignore the fact that Telnet doesn't use UDP, but you get the idea. So in the lecture review session, we'll see this in action. So what we have here is an example of a very, very simple Python program implementing a UDP packet relay. So it'll receive UDP packets and then transmit them back. So this Python program will be running on the Pi, and I'll be using the laptop, my PC, to send a message. It'll be received by this program and then transmitted back to a receiving device on the same PC. So you've got 3 processes running, so I've got 3 programs running. So I've got 2 shells, one transmitting the data, one receiving the data, and a Python program implementing this relay agent. So this Python program needs to know what ports it's listening on and transmitting to. So those ports will be associated with a network interface, and that network interface will have an IP address. Now, I must admit, this always feels a bit odd to me that you don't define the IP address in the transport layer. But again, it makes sense that this is defined in the network layer. So this bit here, you have to know, but it's defined in the next layer down. So our Python program will be listening for incoming UDP packets on port 8000. But that port needs to be associated with a network interface, and that network interface will have an IP address. And for this particular example, it's 192.168.0.254. So this will be one of the network interfaces on our Raspberry Pi. It will receive a packet on that interface. So we can see here it will receive that packet, and then it'll just transmit it straight away back, and that will be transmitting to IP address 192.168.0.100. So this is the IP address of the remote machine. So this is the IP address of the laptop, and it will be transmitting to port 8001. So on the laptop, there'll be a process running, listening on port 8001 for that UDP packet. So your receiving interface, your receiving NIC is on this Raspberry Pi. This IP address is not on the Raspberry Pi. This IP address is where you're sending the data to, your destination machine, your destination host. So to generate UDP packets, we can use the command line program netcat. So what that will do is it'll take in from standard in string. So here I'm echoing hello, piping that to netcat, so it'll receive the string hello. It will then transmit that as UDP packets to the device 192.168.0.254, so the network interface controller on the Raspberry Pi, port 8000. Obviously that program will then receive that, transmit it back to the laptop, to this IP address, this port. So again, have another process running on the laptop, running netcat, which will be listening for UDP packets on the interface 192.168.0.100, port 8001. And as you can see there, it's printing hello within that shell, within that terminal. So this communication process we can capture on the Raspberry Pi by running Wireshark. So you can see these packets being received and then transmitted, coming from 192.168.100, the laptop, going to the Raspberry Pi, and then coming from the Raspberry Pi back to the laptop and the UDP packets. And again, we'll look at all of this in a little bit more detail in the lecture review session. Okay, the final thing to look at is how the checksum is generated. As I say, that will allow you to detect changes within your packet. So has something gone wrong during the transmission process? Was there a sudden burst of electromagnetic interference that caused a bit to be flipped on that copper wire? So there's different ways of doing that. Obviously, so the more complex the algorithm used, the harder the probability is that you can detect these errors. But equally, the more complex the algorithm, normally the more time it takes to process. And obviously, if you want things to be quick, and UDP is a quick and simple protocol, we want to make this a simple checksum generation. So something that can be generated very quickly. Equally, as you saw in the Python demo, when we generate this communication link, our checksum should be able to check whether the data coming in is for us. So what we do in UDP is the checksum is actually performed on a virtual header, a pseudo header, a header that includes the IP addresses, the 32-bit source and destination IP addresses that you'll be communicating between. In addition to our source ports, our destination ports, our length, and our checksum and our original data. As you can see here, there's a little bit of leakage between the various layers, between our transport layer and our network layer, because obviously UDP is in the transport layer, but it knows about the network layer, it knows about IP addresses, but this is included within this virtual checksum. Because obviously the receiving host wants to make sure that this data is for them. So to keep things simple, the checksum is implemented as a ones complement addition. So a very simple thing to do in hardware. So you break down this pseudo header into a number of 16-bit values. So you have a 16-bit chunk added to the next 16-bit chunk. So in your data fields, when we had like hello, for example, you convert the character into its ASCII value. So you'd have a 16-bit value containing the H, which obviously would be 68 hexadecimal, and then the E, which would be 65. And you add those all together and you'll end up with a single number. Sometimes that is offloaded into dedicated hardware, so to free up the processor's time, so you can offload that checksum generation. But the intent here is that it's not a perfect checksum. It doesn't detect all possible error events, but it's a quick checksum that gets most of the errors. So we have an example here of a UDP packets checksum generation process. So 1's complement addition, you might be familiar with 2's complement addition. So what's the difference? Well, it all depends how it handles the carries. So you can see here we have an example. We have two 16-bit numbers being added together. So you just go through the normal binary addition process. But you can see it's generated a carry here. So normally in 2's comp that would be lost, it's just discarded. But in 1's comp we wrap that one around. So we generate this 16-bit result, then the carry is added on to that result. So you never overflow, just keep adding the carries back in. So that's what it's showing this stage here. So the 16-bit result you can see here is repeated here, and then the carry is added onto that result. So that is your final result of the addition of those two numbers. So you generate a 16-bit result. So if you look at this as a hexadecimal value, so you can see they got 0, you've got 2, you've got 9, and then you've got 4. So you've got 0, 2, 9, 4 is the final value for this simple example. So this value is inverted, so the zeros are set to 1s, 1's set to 0, so you can see here. So 0, 2, 9, 4 is its inverted value is FD6B. So this value here will be the checksum that is put into your UDP packet. So that value will be written into that 16-bit field that you can see in the UDP header. So that packet is transmitted across the network, it's received. The receiving host then regenerates the checksum, obviously removing this checksum value from the data it's accumulating. So it'll add it up, and if all's gone well, you should get the same result. So if you add the checksum you've received to the checksum that you have generated on the receiving host, you should generate a result that contains all 1s. If you don't, then the error has occurred and you know that you should discard that packet. Again, to see this one in action during the lecture review session, we'll see how that is performed for an actual packet. So we'll catch some Wireshark packets and then we'll enter the relevant data. We'll look at those data fields that are within the pseudo header. And because my mental arithmetic is not very good, we'll use a simple Python program to add all those values together to confirm that the generated checksum matches the checksum generated, or captured, should I say, in Wireshark. To test if all that made sense, a quick quiz. I would like you to generate a checksum for these 8-bit values, being kind here, reducing the amount of pen and paper binary addition that you have to do. So add together, using 1's comp arithmetic, these 3 8-bit values to generate a result, and then obviously invert it to generate your checksum that would go into this packet. Then consider if the receiving host received the checksum hexadecimal value 65, did an error occur during the transmission of this packet? And a couple of general knowledge questions here. So is UDP a connection-based or connectionless-based protocol? And what happens if a packet is dropped? What would your NTP client do if it didn't receive the data it was expecting? As always, we'll go through these answers in the lecture review session again. So the key thing here is to realize that an unreliable network protocol is not necessarily a bad network protocol. So the advantage of UDP is it's small. You only need 8 bytes in that header to allow you to communicate between 2 hosts. So your ratio between the amount of data, the amount of fields that are in your header to data is small. You've got a small header and a large amount of data typically. It's a very efficient way of transmitting your data between 2 machines. Again, because it's got a small header, it takes a little time to generate and a little time to process. Also, it's a connectionless based protocol, so you don't have to set up a communication channel between the 2 machines, the 2 hosts, before you transmit. You just transmit that packet onto the network and assume that the host were receiving it. Obviously, as this is an unreliable protocol, you don't need to buffer this data after you transmit it. When we look at TCP, you'll see that as the TCP protocol is responsible for retransmissions, obviously it will need to maintain a copy of the original data just in case the data is lost during the transmission, just in case it needs to retransmit it. So there's a lot more state information, there's a lot more buffering required, there's a lot more information needed in the header to allow it to do that. So removing that from UDP means that the processing load on the client and the server is reduced significantly because it doesn't do anything. So if you want a quick, real-time, minimal delays, and you can tolerate a few lost packets, UDP is the protocol for you. But the flip to that, all those advantages are obviously can be considered disadvantages. If you need a reliable connection, if you're transferring a file, for example, then you want to make sure that that complete file is transferred. Otherwise, the file is corrupt. It's no good. But if you're streaming a video, does it matter if you drop a frame or two? I suppose it ruins your viewing enjoyment, but it doesn't break the system. Whereas for some things, you need to ensure that the data gets from point A to point B. Obviously, to get around that, we can still use UDP as our transport layer protocol, and we can push that functionality, the retransmitting bit, up into the application layer. And you do see that for some other protocols. So you use UDP as your transport protocol, and it adds additional error correction, retransmission mechanisms up into the application layer. So because UDP is not a reliable protocol, and have some disadvantages that obviously if a packet gets lost, it's lost. In addition to that, there's no flow control in UDP, so there's no way of detecting if you're sending the data too quickly to the receiving host. So it's very easy if you're transferring a lot of data using the UDP to swamp the network. There's no congestion control, there's no flow control within this protocol. So you can hog all the network bandwidth if you so desire. So if you were to look at the UDP header there, you can see the length field is actually a 16-bit value. So in theory, you could have data packets up to 64K in size. So the length field represents the size of your headers and the size of your data. Now, in theory, big packets, large segments is a good idea because obviously the ratio between your header, which is 8 bytes, and your data makes it a more efficient data communication because effectively you've got almost 64K worth of data and a very small 8-byte header. So it's very efficient. But you've got to remember, in a packet switched network, it's a store and forwarded network. So if you have large packets, that means that each of the routers needs to store this complete packet before it can forward it on to the next hop. So 64K is a lot of memory, so you're hogging the memory in the router. Or another way to think about it, if we go back to our pigeon analogy, a pigeon can only carry so much. So the bigger the payload, the bigger the canister will need to be. So our pigeon will reach its maximum capacity at some point. It can only carry so much. Which reminds me of Monty Python and the Holy Grail. So the pigeons and the coconut... No, not pigeons, was it? It was swallows and swifts. Swallows. It was swallows carrying coconuts in Monty Python. That probably doesn't make any sense to anybody, but that makes me laugh. So these large, or as we would call them, jumbo packets, are not always supported. You typically would use a more reasonable size of data, something smaller. So back in the early days, obviously when UDP was developed, memory within the routers was a scarce resource. Memory was expensive back in the early days when the internet started. For example, my first PC had 1 megabyte of memory, so not 1 gigabyte, not 1 terabyte. It just had 1 megabyte's worth of working memory. So therefore, the people designing this protocol needed to decide what was a reasonable amount of data, and they decided upon 576 bytes. So packets less than or equal to 576 bytes were guaranteed to be accepted, were guaranteed to be delivered, to be stored in your routers, but not necessarily obviously because it's UDP guaranteed to be delivered, because obviously if they're corrupt, they'll be dropped. And UDP segments greater than that, greater than 576, could be dropped if the host or the router couldn't support packets of that size. Obviously, that's a very small value in the context of devices nowadays. So typically, you would see packets around about the 1,500 bytes size nowadays. But it very much depends on your configuration. It very much depends on the hardware in your network. So it's a bit of a trade-off. So do you go for big packets? And to some extent, it's dependent on the reliability of your network. So if your network is reliable and the probability of a packet being corrupted is low, then yeah, you can go to big jumbo packets and make your network more efficient. But obviously, if your network is unreliable, you don't want to be retransmitting, if we're using TCP, these jumbo packets. We would like something a bit smaller, a bit more efficient. Again, if we did go for larger UDP packets, there's an assumption that the lower layers in our network protocol stack could support these, and that's not necessarily true. So the IP protocol, for example, may not support packets of that size, in which case these bigger packets would be fragmented. The lower layers in our network stack would break these bigger UDP packets down into smaller packets that could be transmitted across our network. And we'll see that in the lab. So we'll see an example of how larger UDP packets will be fragmented down into smaller IP packets. And as I say, it all depends what your network infrastructure will support. What is the maximum transmission unit, or your MTU? What will your hardware accept? And as I say, it's around about 1,500 bytes typically. So a programming exercise that we'll be looking at in one of our labs. So we'll have a lab session where we implement this functionality. So we need to write 2 Python programs, one to transmit and one to receive the image of Bob you can see on the screen here. So Bob will be stored in a plain text file. He'll be stored as a ppm image file, the same as we used in sys1. We need to read that file, break it down into UDP packets, and then transmit those across the network and receive them at the other end. So there's a number of decisions to be made here. So how do we transmit that data? How do we synchronize the receiving and the transmitting units? How do we know how many packets should be sent at the receiving end? How do we know if all the packets have been received? What port should we use? Could I use port 123, for example? Is that a free port that my Python program could use? To help you think about that one, here's some screenshots of various fragments from my solution. Looking at that, it's kind of a jigsaw puzzle. Can you join together these fragments of code to implement our transmitting and our receiving Python programs? And as I say, have a think about it, write your own program. I'm definitely saying that this is not the best solution, but how would you implement this program? In my solution, I sent, in addition to the image data, at the start of that transfer, I transferred to the receiving host the image file name and the number of segments, how many data packets I would be sending, breaking it down into 1K byte blocks. But different ways of doing it. You don't have to do it that way, but that's the way I did it. So have a think. As I say, we have one of the practical sessions reserved for this programming task, so you can test out your ideas in the practical. And fingers crossed, touch wood, Bob will be transferred correctly and survive the teleportation. Okay, for now that's where we'll leave our investigation of UDP. As always, we'll be going a lot deeper in the labs, in the practical sessions, looking at how UDP works, capturing UDP packets using Wireshark, etc. But hopefully I've convinced you that UDP is a simple protocol, it's a fast protocol, it's a protocol with low overheads, only 8 bytes in its header to allow you to implement your communications. However, you should remember that this view of your data packet doesn't reflect the actual size of the packet that will be transmitted onto the network. So from a UDP point of view, the size of our packet is just the 8 bytes for the header and whatever your data is. But obviously that reserves no space for your IP addresses. So we need to include the data fields, the headers we need at each stage as we go down our network stack. So the size of the data you'll be actually transmitting will incrementally increase as you go down those layers. Just for a moment to lecture 2, and we look at slide 11, I believe it is here, we can see that our message from the application layer goes down to the transport layer. So we've got our message plus our UDP header. But when we go to the network layer, obviously you need to store the IP addresses that we looked at in our program examples. So our source and destination IP address, that needs to be specified somewhere in our packet. And that will be in your IP header, so in your network layers header. So you can see here that this segment is encapsulated with your network header, with your IP header. And again, if you go down to the link layer, now this packet here, our IP datagram, is encapsulated with your link layer, your Ethernet headers. So this is your Ethernet frame now, made up of your Ethernet header, your IP header, your UDP header, and your actual message. So yes, from the transport layer point of view, this is your header. But as you push down into that network stack, you will be adding other headers. As it says here, so when we get down to the next layer, the network layer, layer 3, obviously we'll be adding IP headers here to store our IP address, the source and destination IP addresses. And as it hints there, other stuff. Again, when we run our Python programs in the labs and capture the packets using Wireshark, you'll see that there's no connection phrase, there's no configuration of the communication channel. It's a connectionless protocol. Your transmitting program will just transmit the packet onto the network and hope that the receiving machine is good to go, is ready to receive. There's no synchronization between the transmitter and the receiver. And as we've discussed, there's no retransmission mechanism built into UDP if an error is detected via the checksum. But all of this from one point of view is an advantage. It makes it very efficient, makes it very simple to implement. Again, finally, as it says there, don't confuse the terminology used to describe UDP in the sense that it's an unreliable protocol. That doesn't mean it's faulty. It doesn't mean there's anything wrong with the protocol. It just means that it's a best effort delivery system. So unless something goes wrong, unless you get an electromagnetic pulse and corruption, some sort of electromagnetic interference on your copper wires that causes a bit flip, this is a reliable protocol. There's nothing fundamentally wrong with it. It's just that in the event that an error does occur, it won't recover for you. That packet will be lost. And that may be critical, in which case, as you'll see in the next lecture, we would use TCP. But if you can tolerate lost packets, then UDP may be the way to go. So UDP is used in a lot of application layer protocols. So ones we looked at already, so DNS, NTP, DHCP, they're all UDP based protocols. One way of identifying if it is a UDP protocol is broadcasts. So TCP, which we'll see later, the transmission control protocol, is a point-to-point protocol. It implements a connection between two machines. You can't do a broadcast with TCP. So if you see a protocol using broadcast addresses, that will be a UDP protocol. So in addition to our ones we've seen previously, there's some other ones. So there's the network boot protocol, BootP. There's the trivial file transfer protocol. We have the simple network management protocol. So a protocol that allows you to send diagnostic information across the network. So it allows your routers to send you information about their loading, their network traffic, etc. We have the real-time protocols. So protocols associated with perhaps voice over IP, and real-time streaming protocols, and you can keep going. Obviously, there's a lot more different protocols that we haven't got time to look at. If you play any online games, what you may have seen at home, if you use Steam, is that you may have had to unblock or port forward particular port ranges. So we've got examples here of 27,000 onwards to allow you to play online games. So if we go to the Steam homepage, we can see what ports need to be open, which ports are being used for the game. So you can see here UDP connections across a particular range for your game traffic. So normally this isn't an issue if you have outgoing traffic from your client to the game server, but if you're hosting your own server on your own local network, then you'll need to port forward. You'll need to configure a router to allow incoming connections on particular port ranges. And these are defined here, and obviously there may be specific ports that particular games use that you need to enable. So I say the alternative to UDP is TCP, so our transmission control protocol, a connection-based, a reliable protocol, a protocol that guarantees that your data will get from one place to the other. So this protocol is a lot more complex than UDP because it has to handle all these edge cases. It has to detect when things go wrong, and it has to have mechanisms in place to resolve these issues. So to do that, you need a lot more processing. You need a lot more data fields within your network packet to handle these situations. So do have a pre-read about TCP if you've got time. It's a lot more complex, so it's significantly harder to understand. So do have a look at that one, and do have a think about that UDP file transfer program, as you'll be implementing that in the lab. And this is a program task for you, so I will not be guiding you through this programming task. It's for you to solve. Obviously, I will give you the solution in the following weeks, but this one here is just to allow you to have some space to actually try and solve this one yourself. Because what I do find with programming with networks, it's very easy to think that you understand something and you then find you actually don't. And you only find that out when you actually try to use the protocols, when you try to program a system to use these protocols. So actually writing a program to use UDP will test your understanding of UDP and how it functions. And this is especially true when we get to the TCP programming task. Radio, so I think that's where I'll leave this one, and as always, I'll see you next week.